Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hello and welcome to Physics with Beth and Beth. I'm Beth. We are in this AP Physics C curriculum. It's also known as the Engineering Physics, that first class in college in your engineering program. We are in Unit 2. This is our first video of Unit 2, which is on Newton's laws of motion. Now, I'm going to go over the laws of motion very quickly, but if you need more detail on it that you've not seen this before, then in our AP Physics 1 curriculum, we have a whole unit on Newton's laws that you might want to look at if you have not seen this before, because I'm going to go through them pretty quickly. So first law is the law of inertia. Law of inertia simply says that an object at rest wants to stay at rest, an object in motion wants to stay in motion in a straight line at a constant velocity unless acted on by a balanced force. All right, basically inertia is that property of matter that it just wants to stay the way it is. If it's at rest, it wants to stay at rest. If it's moving, it wants to move in that straight line unless acted on at a constant velocity unless acted on by a unbalanced force. Not just a force, because you might have equal forces in opposite direction, but an unbalanced net force. All right, kind of like in the morning when the alarm goes off and it's time to go to classes. You're an object and you're resisting that wanting to change your motion. Maybe we just want to stay in bed. All right, so kind of like that. So if I have this sign here says be a vector, it's just going to remain here at rest unless an unbalanced force acts on it. All right, or maybe even better, an unbalanced force, there you go, that tips it over. So that's first law, also known as law of inertia. The second law is that the sum of the forces, or the net force, equals the mass of an object times its acceleration. So in other words, it looks like this, for now anyway, where these are vectors, force and acceleration are vectors. We're going to change this up a little bit as we get into the calculus piece, but not quite yet, so just hang with me on this video. But that sum is our sigma, let me get that out, is our Greek letter for sigma that just means sum. It's the total, or sometimes you'll see this listed as net force as well. Net force, sum of the forces, they mean the same thing. Equals that mass of the object times its acceleration. Now, a couple of things to note in the second law is that force, the direction of force, that's a vector, acceleration is a vector. The direction of your net force is also going to be the direction of your acceleration and vice versa. Also interesting to note that force and acceleration are directly proportional, whereas mass and acceleration are inversely proportional. In other words, as mass goes up and you keep the same force, the same net forces on an object, the same net force on an object, then that mass, if it goes up and increases, then your acceleration is going to decrease. If your mass decreases, your acceleration is going to increase as long as you keep that net force the same. Okay, so that's second law. Third law is known as the action-reaction law. For every action, there's an opposite and equal reaction. And we'll get to that a little bit later. But those are the three laws. So we're just going to jump into problems now. We're going to do a problem with Newton's second law, but we're going to use our unit vectors, which is different from our AP Physics 1 because we didn't have unit vectors in the curriculum. Now, if you remember, a unit vector is going to have an I hat and a J hat. It also, if it's 3D, it's going to have a K hat. But I have two forces acting on an object. Let's say it's a box. And we have two newtons in the X direction, which is I hat. We have 5 Newton force in the J hat, which is the Y direction, so horizontal and vertical. And then we have a second force that's acting on this object that's negative 4.0 I hat plus a negative 2.0 J hat, meaning the X direction or horizontal and that Y direction vertical. All right, now here's what they're going to want to know. Oh, they also gave you that your absolute acceleration, that's what these little lines mean here, that's absolute, that means it's without direction, is 1.50 meters per second squared. Okay, that is without direction. In other words, that's not in I hat and J hat. We're not for sure. We're going to figure that out. in a minute what our direction of our acceleration is. And remember that little trick that acceleration is going to be the same direction as your net force. All right, and then our initial velocity, this object, if it's a box, is moving at 3.00 I hat, meaning horizontal, velocity, which is in meters per second. Okay, perfect. 3 things they want to know. They want to know mass of the object. They want to know the direction of the acceleration, because they only gave me the absolute value without direction. There's no I hat or J hat in that. And then they want to know the velocity at 10.0 seconds. So let's just get started. All right, well, the first thing I see 2 forces, but I need net force in order to use this second law. All right, so I'm going to need to figure out what my net force is. So here's what I'm going to do. I'm going to take F1. I'm going to rewrite this over here so you can see this. I have I hat plus 5.00 J hat, and that's in newtons. And then I have the second force, which is negative 4.00 I hat minus, or I have a plus minus, but we'll just do minus 2.00 J hat, and that's in newtons. Okay, I want a net force. Add up the I's, add up the J hats, the I hats and the J hats. In other words, add up your forces in the horizontal direction, or X, because remember I hat represents X, J hat represents the Y direction, or vertical. All right, well, if I add these up, that's going to be a negative 2.00 I hat. 5 minus 2 is going to be a 3.00 J hat. That's going to be in newtons, and that's going to be my net force. Or you can write it as the sum of the forces. Now I have my net force. You're like, great, that is not what any of these 3 things ask for, so what are we doing? Okay, well, you have to know net force first in order to find the mass. And then what we're going to do is we're going to use this equation. And in fact, I'm just going to kind of wipe this out. So I now know my sum of my forces, and I want to know my mass. And I know my absolute acceleration. Okay, the problem is that I have I hat and J hat in this, and my acceleration is not in I hat, J hat, it's in 1.50, it's absolute. So what I'm going to do is I'm going to draw this out so that you can see this. I'm negative 2, so I'm going to go over negative 2, and I'm up a positive 3, so I'm going to go over here, and this is my net force vector. Okay, so that's my net force, and I'm getting very sloppy on my arrows here. All right, that is my magnitude. If I could find my magnitude, then I can certainly compare the magnitude of my net forces to the magnitude of the acceleration to find my mass. All right, so I'm going to take, if this is 2 and this is 3, that over there is negative 2 and 3. I'm just going to do, hey, if I want the magnitude, I'm going to do my pi bag. We're going to pi bag it. All right, so we've made that a verb in physics with Beth and Beth. So I'm going to take my negative 2 squared plus my 3 squared, and that's going to equal, let's start here first, that's going to equal that net force squared. Or, in other words, negative 2 squared plus 3 squared, and take the square root of that is going to be my net force. Okay? All right, well, when I do that, my net force, again, sloppy with the arrows, my net force is 3.6 newtons. Okay, well, now I can plug that in up here. I now know my net force, it's 3.6 newtons. I'm looking for my mass. And my acceleration is 1.50. Now I'm in the same units. This is magnitude and this is magnitude. Okay, you just can't combine a magnitude here and put in an I hat and J hat here. You have to keep it all unit vectors or keep it all magnitude of the vectors. Okay, so that is my net force. If I divide 3.6 by 1.50, we get a mass of 2.4 kilograms. And there is part A. I have done part A. Check. I like checking those off. It makes me feel good when I have a list and I check off Now they want the direction of acceleration. Okay, that was our little trick. We said, hey, remember, these are the two vectors, force and acceleration. So if force is northeast, acceleration is northeast. If force is southwest, then acceleration is southwest. They're the same direction. Now remember, in physics, northeast and southwest aren't good enough. We want degrees, right? So we're going to figure out the direction of acceleration by understanding the direction of the net force. Well, I'm going to go here. I'm going to do, this is B. I'll go right here to B. All right, I'm going to redraw this. I have my force, my net force, if you remember, is 3 and a negative 2. All right, and my net force, of course, here on this line, my hypotenuse was 3.6. That doesn't really, we don't really have to, I'm not going to use that actually. And I'm looking for that direction. If I can find that direction of this force, net force, then I will know the direction of my acceleration. So that's going to be opposite over adjacent, which is tangent. So tangent theta equals 3 divided by negative 2. So theta is tangent inverse of 3 over negative 2, which comes out to be negative 56.3. And that's in degrees. Okay, why negative? Because I'm in this second quadrant that is northwest. All right, so it's really defining, here, let me go back here. It's really defining that angle. Well, really in physics, a lot of times we want, so you could leave it at 56.3 above the negative x-axis, because that's what it is. That angle is, this is the negative axis, and that's above the negative axis. But a lot of times in physics, we like to call it from the positive x-axis. So we would be looking at this angle from the positive x-axis until you hit the vector. Okay, well that would be this whole distance, and let me do another color. This whole thing is 180. So if I took 180 degrees minus that theta I just solved for in degrees, this 56.3, then you're going to get theta from the positive x-axis. Okay, so that would be 180 minus 56.3 is going to be that theta from the positive x-axis. All right, well, if I do that, I'm going to get 123.7 degrees, and again, from the positive x-axis. So it's going to be from here, my green, from the x-axis positive to where I hit the vector. Okay? So, and if that negative in there confuses you, just know that you're looking at opposite over, I mean, it is negative 2, but you're looking at opposite over adjacent. So if you kept if you didn't put the negative, in here, you would get a positive 56.3, but remember that's coming from the negative x-axis. All right, perfect. Now that's B, done. We want to check that. We love that because remember the direction of the force is the direction of the acceleration. So once we found the direction for force, the net force, I should say, then we have the direction of the acceleration. Now, the third thing it wants is the velocity at 10 seconds. All right, well, I'm going to just draw the line here. Velocity, we remember from our big 3, is initial velocity plus the acceleration times time. They said that they want to find it at 10 seconds, so I know that. They told us our initial velocity, and they actually gave it to us in I hat, was 3 I hat, meaning 3 in the positive x direction or horizontal. So my velocity looks like this, 3.00 I hat plus my acceleration times my time, which is 10. And I'm looking for this final velocity after 10 seconds. Okay, well, all now I need is my acceleration in I hat and j hat, because I can't just put in 1.5 here, because that's what they gave me, but that's absolute. It's like a magnitude. It is not in I hat j hat form. And you can't take a magnitude and add it with an I hat j hat. Those are two different forms of vectors. So we're going to need to find acceleration in an I hat j hat format. Well, how do you do that? Okay, this is how you do it. You're going to start, remember, acceleration, we're going to rewrite this F equals ma, and now we're going to say, hey, my sum of my forces divided by my mass equals my acceleration. I know my net force. I found it right here. This is my net force in I hat j hat, because remember, that's the form I'm looking for. So I'm going to take that negative 2.00 I hat plus 3.00 j hat. That is my net force. I just took I hat and j hat here, and I'm going to divide it by the mass, which I found in problem A, which was 2.4. And I'm going to get my acceleration. So let me actually erase this down so we can look at this. All right, I'm going to erase this over here so we can kind of see this. Hopefully we get all that. All right, so now what that's going to be is negative 2.00 divided by 2.4 I hat plus 3.00 divided by 2.4 j hat. And that's going to be my acceleration. Perfect. And did I write that down? I did not. So I'm going to pull this up here so we can see that. That's going to be, because I did not write that down, that is going to be negative 0.833 I hat plus 1.25 j hat equals my acceleration. All right, and then that's actually meters per second squared, so you see that. Okay, now I can use that formula I had up here, 0 plus V naught, plus acceleration times time. So that velocity at 10 seconds, my initial was 3.00 I hat. My acceleration is negative 0.833 I hat plus 1.25 j hat. And I'm going to multiply that acceleration, and all these are vectors, acceleration times time. Time is not, but 10 seconds was what that was. So now my velocity at 10 seconds is 3.00 I hat. I'm going to multiply 10, distribute that 10 to both pieces of my acceleration, my horizontal direction and my vertical direction. That's going to be a negative 8.33 I hat plus 12.5 j hat. All right, all I did was distribute the 10 here and the 10 here. Now all I do is add up my i's and I add up my j's, which there's only one. So my velocity at 10 seconds is negative 5.33 I hat plus 12.5 j hat. And that is my velocity. If they'd asked for an absolute, if they said, hey, what was your absolute magnitude of your velocity at 10 seconds, then we know how to do that. I'm not going to do it, but we're going to, because of time, but this would be negative 5.33, and this would be here, and this would be 12 here. And then you could do your Pythagorean, 12.5 squared plus negative 5.33 squared, and take the square root of that to find the absolute value. Okay? That's all it would be if they wanted magnitude. But oftentimes you can leave it like this. Now, we need to do some thinking here and some logic real quick before I let you go. Does this make sense that this object was going 3 meters per second in the x direction only at the very beginning, and at the end it is now going in the negative direction in the x direction and positive in the y direction or vertical? Does that make sense? Absolutely. And why? Because our net force was in the negative direction in the horizontal and positive in the y. So it makes sense that that net force caused this to, it started in the positive horizontal, but it ends up in the negative horizontal direction with Y direction now. It's now two-dimensional motion, whereas before it was one-dimensional. Perfect. The other thing that you would want to check, possibly if you had time, was this acceleration. We broke this down into an X and Y component, but the magnitude of this should be negative 0.833 squared plus 1.25 squared, and take the square root of that, because that is the X component and the Y. So again, it would look like this with a 1.25 in the Y and a negative 0.833 meters per second squared in the X. And if you did that and found this little magnitude here by this squared plus this squared and take the square root, you should find that that acceleration and the magnitude is 1.50 meters per second squared, because they gave us that. So that's a good check, and it does come out to be that. All right, that's it. That was a lot, but we just took Newton's 3 laws and then applied it to find mass, the direction of acceleration, and a velocity after 10 seconds with a two-dimensional object using unit vectors. So thank you for watching. Thank you for listening to all of that. And if you haven't subscribed yet and you like these videos, we would love for you to do that. We're going to be issuing new videos every week now from until this curriculum is done. So that will help notify you of that. And tell your friends about them. If you're enjoying these and they're helping you, we would love for you to share our channel with your friends. Thank you very much, and happy physicsing.